Welcome. In this video, we will learn about different types of aquifer, which are mainly confined and confined aquifer. So by the end of this video, you will be able to define some key aquifer terms like what is water table, what is bathymetric surface, what's a confined aquifer, what's an unconfined aquifer, what's an artesian well, uh, what is capillary fringes, and like these keyword, yeah. You you should be able to differentiate between the properties of different like confined and unconfined aquifers. And then you should be able to differentiate water tables. Water tables that's associated with unconfined aquifers. That's where the water sets the top of the aquifer, while bathymetric surface that's associated with confined aquifer, and this tells you about the pressures of water pressure inside the aquifer, how the water is pressurized inside the aquifer. So this would be more like when I studied like groundwater hydrology, it was not actually like this. It was more like it was very quantitative. It was more like a mass class. Um, but here I try to make a balance between like quantitative, like I don't want to turn this to a math class. And one thing I'm doing here is that I would like also to give you this not just like a quantitative groundwater hydrology, but to give you this qualitative understanding, because this qualitative understanding is very important. So this lesson would be mainly like qualitative understanding to so you can absorb and some key terms and concept in groundwater hydrology. Okay, so it's a very important lesson in my opinion. Yeah. So again, that's your Facebook or like social media exercise for this video. You have to do this in addition to exit ticket. So these are two things. So you have to do this one, and then you also have to do exit ticket. Exit ticket is just like a student to an instructor, the discussion, while these ones are more like student to student discussion. Yeah. So you need both. Like you need the student to an instructor and student to student, and then the instructor will also comment on this one, and thus you close the loop. Okay, so let's get here. Let's start. What let's just start like what's an aquifer, like so you hear this term like aquifer, aquitar, aquiclude, and aquifuge. What are these terms? So aquifer, we know this, like that is a subsurface water storing unit. So what this will distinguish an aquifer, yeah, that's what will distinguish an aquifer would be mainly, me start writing here. So what will distinguish an aquifer will be mainly like the permeability. It has high permeability. So you generally find like the permeability or like hydraulic conductivity value of if K is larger than 0.01 meter per day, and you can check like the previous lesson to learn about this would be like sand or fine sand or 10 to the power minus 7 meter per second, then that is an aquifer if it's larger, where permeability measures the availability of porous material, soil, sediment, or rock to transmit water. Thus, aquifer, it store, transmit, and yield water at rates fast enough to supply reasonable amount of wells. So that is an aquifer. So if you want to have a well, make sure that your well is tapping through the aquifer, not an aquitard. What is an aquitard? This is a subunit. It's also referred to as a confining unit or confining layer or leaky confining layer. We will know what does leaky confining layer means. Like let's say here is that's your aquifer, and that is your confining unit. A leaky confining unit would be a unit that will have leaks. So let's say this is your aquifer, and maybe you have like a unit here that looks like this, and the unit here that looks like this. So this is a confining layer, this is a confining layer, and then there is a leaky area, like some sand here where water can leak. But still, like, and this would be like a confining area, and this is an aquifer. So this is your aquifer where it can hold, store, store, transmit, and yield water, while an aquitard would be non-confining layer. And so the aquitard, it is refer to that slow, like water moves slowly, and but it does not prevent water from passing. So water, like water, the water flow in the aquitard, but flow very slowly, but it does not prevent water from passing. So you can get some uh, very little amount of recharge through it. Yeah. So again, what would be the main feature of this? This low permeability. So you'll get a K value less than meter per day. That would make like an aquitard. Yeah. Now you have like these terms also like aquiclude or aquifuge. These are impermeable layers. So this is like a very impermeable aquitard. So this is called aquiclude or aquifuge, impermeable confining units with ultra low or no flow. That would be like aquiclude or aquiclude. These terms are not generally used. So example of this one, for example, would be like a piece of granite or marble or igneous rock. So that will, how will water flow in a piece of granite? Almost no flow, yeah? Ultra low or no flow. Okay. So let's look here. Let's look at an image. Maybe an image will help you to understand this better. So here, uh, this is your land surface. Yeah, you have a tree here, and now this would be like the unsaturated zone. So this is the unsaturated zone, and this would be the saturated zone where you have your, this is would be the saturated zone where you have your groundwater. So the groundwater that start with your water table. So all this is the saturated zone. It is sand. So sand has a high hydraulic conductivity. So water can will generally like flow here. Now you have shale and clay. Remember shale and clay, they have a very, so this here has a high hydraulic conductivity. Here this has like a low hydraulic conductivity. So this is an aquitard, which means that water does not pass through here. It passes through here, it flows through here, but at a very, very small rate, like very slow. So you might find some little, tiny little recharge that will happen over like tens or hundreds of millions of years that will here. But then this would be an aquifer, which is above this, there's an aquitard. So this would be like confined aquifer because there's no confining units, it's directly connected to the land surface. This is a confined aquifer because there is an impermeable unit above it. So that could be like sandstone, it could be sand or whatever. It has also high hydraulic conductivity, and then like the water will flow in this way. This would be an aquifuge, that's like a crystalline rock. So there is almost no flow here. Like that would be like there would be no flow here, but here there would be some flow. Okay, so this is just a visual understanding so that you will know like these different terms. So here, let's go again. This is the unsaturated zone. This is the saturated zone. It's an unconfined aquifer because directly uh, connected to the land surface. Then you have a confining unit with low hydraulic conductivity, and then you have this called like a confining unit, and then here you have a confined aquifer or aquitard. Okay, so let's look more here. So, and again, keep in mind like these terms could be relative. Yeah, their meaning could be also relative. So an aquifer, like commonly used unit name, like we use the name aquifer, unit name aquifer, permeability is high. It can store water, it can transmit water, it can yield water. It stores and yield water. Yeah. Example would be sand and gravel. Yeah. And that's like if you want to have a pumping well, that's where like you want to have a pumping well, uh, like you want your pumping well to tap through this unit. You don't want your pumping well to be here because here that does not transmit water or yield water at a significant level. Yeah. So you want your pumping well to be here, not here, or to be here at this confining unit because so like you put your pumping well here so you can tap water from here, you can tap water from here, but here that will not yield much water. Yeah. So like then you have this confining layer, yeah, or leaky confining layer or confining layer. So the unit names that would be Aquitar. The permeability would be low. It can store water. It can transmit water. It can yield water, but it's very slow. Yeah. So allow seepage, but does not yield much water. It does not yield water. Example would be clay, shale, sandy clay. Confining unit, that's again would be like a confining unit. That's aquiclude. This would be permeability, that would be impermeable. It can store water, yes, it could have some water in it. It can transmit water, no yield water, no. It has no flow and no yield. Highly porous but not permeable. Example would be clay. Now, confining unit, again, that would be like the commonly used name, and the unit name would be Aquifuge. It is impermeable, it does not store water, it does not transmit water, it does not yield water, neither porous nor permeable. Example would be like granite or basalt, like unbroken basalt, like fresh basalt, yeah? And keep in mind the relative meaning of these terms. Okay, so these are just like some important meanings for you to know. Now, let's now get into learn more. That's like the main part of this lesson. So the main part of this lesson is basically to learn more uh, about main part of this lesson is to learn more about confined and unconfined aquifers. That's like the most important part of this lesson. So let's look at this. Let's make this more like a thinking exercise, like a thinking experiment or like a critical thinking exercise, and let's do it together. So you see here in this image, uh, so here like you have like the land surface, like you see here, like you have like this is like your land surface. This, what is this? So this is an unconfined aquifer because it's directly connected to the land surface. This would be an aquitard, like a confining layer, yeah? And this would be another aquitard, another confining layer, and this would be like your bedrock. And between two confining layer, what do you find? You find your confined aquifer. Yeah, so that's your confined aquifer. So what do you think would be like the difference between these two aquifer, like the confined aquifer and the unconfined aquifer, I mean, and the confined aquifer? Well, of course, the most obvious difference is that the unconfined aquifer, it is connected to the land surface. So what does this mean? So let's look at this in detail. So this means that it is connected to a land surface. This means that it has like a water table. We call this water table. Why? Because you will have here, you will have like rainfall. Some of this water will evaporate. Some of this water will infiltrate. The infiltrating water, some of the infiltrating water will make it and recharge this aquifer. What does this mean? This means that this water table goes up and down. Like this water level here, it is not constant. Like if you have a recharge event, it will go up, the water table will go out. If you have a drought event, the water table will go down. If you are doing pumping, like you start to pump this water, the water level or like the water table will go down. That's one thing. Another thing is that like this water table could be connected to your surface water body. So you see here, this water level is directly connected to the lake. Versus here, this lake is disconnected from this aquifer. Even though this aquifer is under this lake, they are not connected. Like the water level here in this lake is not connected to here. So let's see, for example, like during drought period, like this is your water table. Yeah. During drought period, this water table might go down. Could be. Oops. During drought period, this water table could go down maybe something like this. Yeah, that could be like your new water table during drought period. What does this mean? This means that this lake will dry. Yeah. Why? Because let's say like this is the groundwater flow direction. Yeah, so this is like your flow direction here. So let's say this is your flow direction here. What is your flow direction here? Your flow direction here is that this groundwater will feed this lake, because you see here like this water table like is above like the lake level, so you will see that this groundwater here will feed this lake. What about here? See, like the lake level is about like your groundwater. So in this case, like this lake will feed the groundwater. So this is a very interesting lake. In one side, on the upstream, it is like a gaining lake. On the downstream, it is a losing lake. How about this one, like this stream here? So like you see, this is your flow direction. Here, your flow direction here will be like this. So, and your flow that because you have like the groundwater level is higher here and the groundwater level is higher here. So the flow direction here will be like this. So this is a gaining stream from both sides. So like from both sides, this is a gaining stream here. In this example, like this lake is a gaining lake from this side and it's a losing lake. So gaining lake, it gets recharged from groundwater. We call this base flow. And the lake water will recharge the aquifer in this direction, in the downstream direction. Okay, so that is one important aspect to note that uh, this, like an unconfined aquifer, it has a water table. This water table could go up and down, yeah, and it could be connected to your, in most cases, in most of the time, it is connected to your surface water body, yeah. Many cases, yeah. In arid regions, they might be a little bit different, but in most cases, it could be connected to surface water body. Okay, so here, if I make like a water well, like or a piezometer here, where would be my water level? My water level would be here. Yeah. Uh, So that is basically the most important thing on about like the unconfined aquifer. If you start pumping from here, like let's say I make this water well and start pumping, guess what will happen to my water level or my water table? So my water table, like if I start pumping from here, I will create like this cone of depression. So you see my water table will start to drop. Yeah. So this water table will drop down to here. But what does this mean? This means that like an unconfined aquifer, it is susceptible to pumping. So let's say I start pumping here, then my water level, like let's say one, I have this pumping well here. I start pumping here, then the water level will go down. Let's say my neighbor has like his pumping well, he like small pumping well. See, it will become dry because the water level will drop, the water table will drop. So this well, like here, for example, will become dry. Yeah. So the water table is susceptible, very like sensitive to pumping or susceptible to pumping, but it's also susceptible to contamination from land surface. So if I have, let's say I have a gas station somewhere here, yeah, if I have a gas station here, and any gas station will have like a tank and there's a ground, and this tank could leak. And once it leak, what will happen? It will contaminate my groundwater, my unconfined aquifer. But will it contaminate this one? No way. Because why? Because this is a aquifer, the confining layer. Water does not flow through here. And even if flow from here, it will be very, very slow. So like to reach here, that might take like a million year or 100,000 year or whatever, because this has a very, very small hydraulic conductivity. Remember, hydraulic conductivity is less than meter per day, and it could be smaller. So, so this is susceptible for like drought condition, is susceptible for pumping, is susceptible for like any contamination from the land surface. Like you have like an accident here, an oil spill. Again, it will be contaminated. Yeah. Similarly, any contamination in lakes or stream, if it is like a losing lake or losing stream, that could also contaminate your groundwater. Versus a confined aquifer, that is not the case. Yeah. So that is the main thing that we need to learn about confining aquifer. Unconfined aquifer, it does not has a water table. Unconfined aquifer, water here is under pressure. So like this confining unit, like you saying this is a sandwich that like is squeezing this unit. So water here is under pressure. So if I make a hole, so water here is under pressure. Water here is not under pressure, very little pressure. But here is under big pressure. So if I make a hole, guess what? The water is under pressure, so the water will gush out. Let me change the color maybe. What will happen is that if I made a hole here, the water will just gush out here. Yeah, until here, until it reaches here. So what, like this pressure that like this water is under, we don't call, so this one has a water table, this one does not has a water table. This one has what we call like potentiometric surface. So potentiometric surface, this is not a water table, but this is like is energy or like the pressure that you have at like a point, yeah. So basically, so if, like, let's say if I make a hole here, yeah, so I make like this hole here, I puncture this aquifer, water will rise up till here. If I puncture, like, let's say I make a hole here, oops, water will rise up till here, yeah. If I make a hole here, yeah, make a hole here, water will rise up till here, it will go to the surface, yeah. So when water goes to above like the land surface, we call this like a flowing artesian well. That's like an artesian well. So we call this a flowing artesian well or simply artesian well. So an artesian well means that, so what does artesian well means? It means that my potentiometric surface or like piezometric surface is above the land surface. When I have my potentiometric surface uh, is above the land surface, then this is like an artesian well. But let me tell you something here. How does this guy get recharged? This guy get recharged from here, from the land surface, directly from the land surface. That's how your water table will rise. How about this guy? How this guy get recharged? It could get recharged through the aquetorrent, but that's very slow and that's like not the main recharge mechanism. So that could take maybe like hundreds of years to get recharged through like an aquetorrent. Like, so water will flow from here to here to here until it recharges here, but that will take like hundreds of years, yeah. But the main recharge mechanism would be through here. That's where it gets its most water, like through here. So you have like rainfall here through this unconfined part, and like through here, water will get recharged and it will flow through here. And that's why this aquifer, it recharge, it could take like hundreds or thousands of years to recharge an aquifer like this, like confined aquifer. It has a very high water quality, but the recharge time it's not renewable. Generally, wouldn't be renewable on a human time. Not generally, but in many cases, it will not be renewable on a human time scale. It's only renewable on a geological time scale. Like, so, for example, I worked before on an aquifer in Louisiana. It's called like the Southern Hill Aquifer. So this aquifer is Louisiana all the way up till the coast, like to the Gulf water. This aquifer got recharged from Arkansas. Yeah. So it gets its water from Arkansas, and this water that we get in Louisiana, it has been flowing for like tens or hundreds of years, thousands of years. Do we have an example like this in here in Florida? Can you think of any example here for an unconfined aquifer that takes like long time to recharge? Well, the Floridian aquifer. Remember the Floridian aquifer which underlies the state of Florida? So this aquifer was recharged mainly during the last glacier period, like more than like 10,000 years ago, and it gets most of it's like under Florida. It is like it would be a confined aquifer. It gets its recharge maybe from like we get its recharge from Georgia or Alabama, like upstream from Georgia or Alabama. That's where it will get recharged, and this water will flow under Florida. So that's would be like a confined aquifer where you have is like have these two confining layer, and water here is under pressure, and we will study like now again this is just like a qualitative understanding. We will study this quantitatively later on in the next chapter about groundwater flow, and we will look at more example. But this is just a qualitative understanding. I want you to understand like the difference between a unconfined aquifer and confined aquifer. So confined aquifer directly get recharged from here. This one will not get directly recharged like from the land surface, but will be recharged like somewhere upstream from here. So like, for example, like this is an interesting thing. You see here, this in this part here, like see this part here, or like this part here, this is an unconfined aquifer, but once it's here, then it becomes a confined because you have two confining layers here. So this is unconfined, like this part is unconfined where everything here, this is a confined. So again, like it's also, these terms are relative. Okay, so water table. So water table, what is this? Now let's do another important thing. Like now we learned what's the difference between unconfined and confined. Let's now learn what's the difference between like a water table and a potentiometric surface. So water table, what is the pressure here? Like, so what is the pressure at this point, for example, in this lake here, or at this point, or at this point, or at this point, at this point? What is the pressure here? Well, the pressure here at any of these points, that would be the atmospheric pressure. So the atmospheric pressure, we generally call like, it's generally like the standard atmospheric pressure. We generally consider this like 1 atmosphere, or like in mercury, like 760 millimeter of mercury. Or you can measure it also in Pascal or like millibars. Yeah, but it's generally like 1 atmosphere. Okay, that's like is a standard pressure. And generally, like instead of using like the standard atmospheric pressure, like, or whatever pressure is here, we generally use something called like zero gauge pressure. So we basically subtract the atmospheric pressure, and we assume that like the pressure here is zero. Yeah. And we call this like a zero gauge the pressure. So instead of using a standard value, like what is the atmospheric pressure at here, because the atmospheric pressure is not constant. Like the atmospheric pressure, for example, in Florida, which we are at the sea level, it would be very different than atmospheric pressure at Boulder, for example, which is 1 mile above or 1 mile above sea level. So as you go above sea level, as you go higher in elevation, the atmospheric pressure will decrease. That's why, for example, in Boulder, you have less oxygen than here because there is less atmospheric pressure. So the atmosphere cannot hold oxygen. Oxygen will escape. If you go, for example, to the Himalayan mountains, you don't get 1 mile above sea level. You get like 8 kilometers above sea level. So some of the peaks there in the Himalayas, they are more than 8 kilometers above sea level. And that's why in this region, if you ever went to any of this region, you will hardly be able to breathe because there aren't like sufficient amount of oxygen. You get much less oxygen than you get here because the atmospheric pressure is much less. But generally speaking, in order to avoid, like what we generally do, we do something called like gauge pressure. So gauge pressure is that we will just subtract whatever the value of the atmospheric pressure is, like high or low, we'll just subtract it and assume that the pressure here is zero, and this is, we call it like zero gauge the pressure. Yeah. So this is a common practice to define water pressure at any air-water interface to be zero. So I define like the pressure here to be zero, the pressure here to be zero, the pressure here to be zero. Again, when I say zero pressure, this is not, there is the pressure of the air column above it, but I subtract this pressure of this air column above it, and I call this zero gauge. Yeah. Okay. So the zero water pressure mean water pressure equal to existing air pressure, basically. So this means that the water pressure here is equal to existing water pressure, and this is zero gauge pressure. Okay. So that is the water table. So water table, by definition, it has or water level, like water level here, or this is also part of the water table. So your water table, this is your water table. It goes all the way to the like stage of the river and stage of the lake. So this is all your water table. And by definition, this is by definition this is the elevation. This is the elevation where your aquifer sit or your water sit, and by definition, this is pressure. This is zero gauge pressure, which means that the pressure equal to the existing air pressure above this air-water interface, like this air column above it. And as you go higher, this air column will be shorter, and accordingly, this pressure will be zero. But again, we will assume whether you are at the Himalaya or whether you are here, you will assume the pressure here is zero because it's zero gauged. Okay. So, a potentiometric surface, this is not the elevation where water sit, but this is the elevation where water will rise. So if I make a hole here, This is where water will rise. But where water sit here. Water sit here. So water sit here. So this is not the elevation like water table. This is the elevation where water sit, but this is the elevation where water will rise. So if I make a puncture here in the confining layer, water will rise up till here. And it measure pressure within this aquifer unit. Like so, does not measure like air pressure. Like it measure like the pressure within like this aquifer unit. Like how much pressure at like this point, yeah, or at this point or at this point. So basically, that would be like the pressures that this is measuring. So if I make a hole here, that's my surface here. Like somebody, if you are sharp in observation, you might tell me, oh, why this water didn't go all the way up till here? If this is the pressure here, because remember, it will part of it will go up to here, but then it will fall by itself by gravity. So that would be the maximum point, but then it will fall upon itself by gravity, and that's why you see. But that's the theoretical level where the water will reach, because that's like the pressure that you have at this point. Um, so like pressure is like you are measuring the pressure inside the aquifer. This pressure is coming because the water is compressed. Like you have these two confining units, they are compressing the water. So water here is compressed. And that is the main storage mechanism here. So that's very important. We will learn this in detail next lesson. The main storage mechanism in the aquifer in this aquifer is that water is compressed, like you compress the water. While so if I start pumping from this aquifer, the water level will not go down. Like this water level will not go down. What will go down would be the potentiometric surface. So if I start pumping from here, like let's say I start pumping from here, the water level will go down. I will dewater this aquifer, I will drain this aquifer, I will empty these pore spaces. Versus if I pump it from here, like let's say I start pumping from this well, what will happen is that like this potentiometric surface will go down. I will just lower the pressure. The water level here will not change. The water level here will be the same unless I emptied this aquifer, which is like well, not generally the case. But what will happen? Like when I start pumping from here, what I do, I don't. The water level here will remain the same. Whatever water level you have here will remain the same. What will decrease is that I will this potentiometric surface will decrease. Why? Because I like this water is compressing and I'm releasing this compressed water, but the water will remain here. I'm just releasing water. Like imagine like you have water, you are compressing this water, then you are taking some of this water. What will happen? The water will expand, but the water level will not go down. Yeah. So that is like a very important distinction that you need to know. And the next class we will like do this more quantitatively, and we will quantify different, like we will understand aquifer storage mechanism, like how here water is drained by gravity and I de-water the aquifer and empty the pore, while here the water level are not changing and I'm just lowering this potentiometric surface. So pressure level is higher than water level. So here, like you see the pressure level, this is the water level, this is the pressure level. The pressure level is higher than the water level. Pressure built up due to this confining unit. So that's we talked about this. Uh, and this pressure that is built up inside the aquifer will force the water to flow. Like you have this pressure, like high pressure, this will force the water to flow. If you puncture this will cause the water to flow upward. Yeah. Okay. So now, giving this definition, let's remember at the beginning of the semester, I told you groundwater table. Like some people define groundwater table as the area where you have like fully saturation, and I told you this is wrong definition because the capillary fringe is also fully saturated. But we define groundwater table, not the area where you have fully saturated, because here you also have, you could have also here in the capillary fringe zone, this could be fully saturated. So let's look at here. So this is the zone of variation, the Vado zone, where you have like soil and water. So if you make a close up, like you take a close up here, you will have like three phases. You have a solid phase, you have a water phase here, and then you have an air phase here. Yeah, so this is air and this is water. If you look here close up at the capillary fringe, actually it would be fully saturated. You will not find any air. But we don't consider this groundwater. And I told you the definition of groundwater is that where you have like atmospheric pressure, when your pressure, like you have zero gauge pressure or like the atmospheric pressure, like like so this is the point where you have atmospheric pressure. And then the saturated zone or the groundwater zone or the zone of saturation is where groundwater flow. Here you will only have two phases. You will have like a solid phase and a water phase. Yeah. Here you only have two phases. Now let's look at this in more detail. So the the definition of a groundwater is that where you have like the pressure here, like at any point here, is equal to the atmospheric pressure. Or if you subtracted the atmospheric pressure, that would be zero gauge pressure. So the pressure here is zero, like zero gauged pressure. That is the definition of the water table. The capillary fringe, you have a negative pressure, negative sucking pressure. Even though this zone is fully saturated, but you still have a negative pressure, and that's why we don't consider this groundwater, because this you have a negative sucking pressure. Negative sucking pressures, this is like a sponge, like sponge effect. Like if you have spill in your kitchen, what do? You put a sponge and the sponge will suck the water up. This is a capillary effect, or like, and that's why we call this capillary fringe or capillary effect. So, and what will characterize this capillary fringe is that it is fully saturated. It is fully saturated, but it has a negative pressure. Again, negative zero gauge to everything here. Like it's yeah, it would be negative zero gauge. Above the capillary fringe, you can find like the pressure could is also negative, but it could go up and down, like it fluctuate. Yeah, it's not, and this fluctuation depend on the soil moisture. Like why? Like you see here in this zone, you don't see like fluctuation. It just keep decreasing. It does not increase and decrease. So like here, this is the most negative pressure you have, and they keep decreasing until it reaches zero pressure here. But above here, it could increase and decrease depending on the soil content, like the degree of saturation, like you have more air and more water. Below the water table, the pressure will increase, because that would be the pressure here would be like you learned it in fluid mechanic. The pressure here would be the height of the water column above it. So here's the height of the water column is like zero. That's why you have zero pressure. This is the height of the water column, like here. So you have like that pressure. Here is the height of the water column, and here, for example, like at this zone, you will have the maximum pressure, because remember, pressure is like rho GH. So here H is zero, so the pressure is zero. Here H is like maximum, and then the pressure would be maximum. Yeah. Here H is maximum, the pressure would be maximum. Okay, and you can review this from your fluid mechanics course. Okay. Now, let me, so that's a very important distinction. The zone of saturation, like groundwater, the definition of water table is that where not where you have saturation, but where you have zero gauge pressure. Because let me, do you want me to confuse you more? Sometimes in this saturated zone, you might find some air. Can you believe this? Even though it's called saturated zone, and by definition there is only solid and water, you can still find some air, but that wouldn't be air similar to here. That would be air bubble. And you can make this experiment, like get a bottle of water and shake it. And sometimes, when you shake a water of bottle, like the bottle is fully saturated with water, yeah? There's no air, but sometimes inside this water, you will find some air bubbles here, yeah? Some air bubbles here. So even this saturated zone, it could has air, but it's different than this air, because this is our air bubble. But that actually could be interesting. Like if you are doing a column experiment and you are injecting tracer, you know what? This tracer could just go inside this air bubble. And then like you inject the tracer, you expect to get the tracer out, and then you find that your tracer is disappearing. And you say, oh my God, where is the tracer disappearing? Is there like a ghost inside my column that is like taking out, like eating up my tracer? Or is there maybe somebody who's sabotaging my experience at night, like he come and steal my tracer? And you could think of all these weird things, but all these illogical or rational things. I mean, rational or irrational, but actually there is a rational reason for this, which is that there are air bubbles, and these this air bubble becomes saturated with your tracer. Yeah, that's why you're not recovering all your tracer. But so again, like to make this story short, like what you need to learn here that this is a definition of this one. Let's look at this example. Like, so I'm asking you here, where is the flow direction? And remember, the flow direction is usually from high head to low head, from high energy to low energy. So where is the flow direction here? So let's study it like one by one. Let's see the head one by one here. Yeah. So this is obviously an unconfined aquifer, but it's connected to the land surface. What is the head here at this point? And again, like this is just, we will learn this in detail like in the next module. Yeah. What is the head here at this point? So the head here at this point, let's say this is my reference level. And from this reference level, that's where I will start like measuring my elevation head. So remember, like from fluid mechanics, there is like elevation head and like there is pressure head. So that's like my zero level. So what is the head here at this point? So the head here at this point, that would be like your pressure head. So that would be like rho gh, like like this much pressure. So yeah, and here, so that would be like the pressure head plus the elevation head. So the elevation head, that's my zero, so that would be negative here. So basically, uh, that's why I get here. What about this one? So here I have like, so that would be like the pressure here, like my pressure here, like the pressure here, which is like rho gh. What's my elevation head here? My elevation head here is zero because that's my reference. How about this one? So here I have like, this is my pressure head, and this is my elevation head. So I add this one and this one. How about here? So here my pressure head is zero, yeah, because H is zero, so my pressure head is zero, and then I have this elevation rate. But all these are equal. So where will groundwater flow? Remember, groundwater flow from high head to low head. So here groundwater will not flow. It will be stagnant. Yeah, because the head here is equal to the head here, is equal to the head here, is equal to the head here. So there's no energy gradient, and water flow by energy gradient, so you will not see this energy gradient. Okay. Let's look more. I'm just showing you, like I'm just repeating over and over to show you like this in more detail. So here, like this is what will happen. You will find like precipitation, and after precipitation, you will have some evapotranspiration, some AT will occur here. And after this evapotranspiration, some of this water will be also like used by plants, so that is, so some of this water will evaporate and some of this water will be used by plant transpiration, and the rest of this water will just go to here, become like a capillary fringe, and this capillary fringe will recharge my groundwater. So this is like the unsaturated zone, this is the capillary fringe, and this is my water table, and this is like this is the rainfall, and this would be like recharge to the water table. So this is called recharge, like how much I'm recharging my aquifer. So you have precipitation, you have infiltration, and then you have recharge, and that would be your saturated zone. Saturated zone, that would be below the water table. So what is the definition of the water table? That is like, here the pressure here is equal to atmospheric pressure or zero gauge pressure. Like the pressure here would be like zero, pressure is zero gauge, or the atmospheric pressure. Above the water table, that is where you have the unsaturated or partially saturated, like you'll have negative pressure. So the pressure here would be like negative, and the pressure here would be positive, and the pressure here would be zero. Yeah. The capillary fringe, this would be the area above the water table, and this capillary fringe zone, that would be different. So the capillary fringe, for example, for gravel, for example, like remember, like gravel, these are big particle size. So big particle size, there will not be very big suction, because this suction depends on surface tension. Yeah, that's how this suction occurs. So the capillary fringe, if you have like a gravel here, the capillary fringe would be maybe few centimeters. Yeah, or few millimeters. If that is sand, the capillary fringe, you have like more tubes, they can suck water better. like more surface tension and they can suck water better. So the capillary fringe could be like instead of like millimeter scale, it could be like centimeter scale, like half a meter. Like if this is gravel, the capillary fringe here would be like millimeter scale. If this is sand, you know, the capillary fringe here could be like up to half a meter or something centimeter scale. If this is clay, like you have very tiny little particle, this capillary fringe zone could be several meters. So that could be in an order of meter. So in gravel, the capillary fringe zone would be millimeter. In sand, the capillary fringe zone would be an order of centimeter. In gravel, the capillary fringe could be up to several meter, like 5 or 6 meter of this capillary fringe zone, like negative pressure before you get to your groundwater. Okay, so that's also something to keep in mind. Again, I'm just like, see, like this is all qualitative now, and later on we will do like in other module, we will do this quantitatively. But just for now, I just want you to have this qualitative understanding because that is important. So here, water table, we talked about this already, but I'm just showing you here. Water table can go up and down. Uh, so that is so the water table could go up and down. So here, for example, this would be like, see, that's your stream level, and this is your water. Sorry, that's like your that's here. That is so that is like the normal water table, and that would be the normal like stream level. And with this normal water table, you have a well here. You can tap through this water. So this is like your water table. You see here when you start pumping, the water table will decline. But like normal water table during the summer, you see what will happen during the summer. The water table will like go down. So during the summer, like your water table could go down, your stream level will go down, and this will become a dry well. Yeah, because your water table is here. So that will become a dry well. During drought period, your water table could even go much lower, and as your water table like go much lower, guess what will happen to this stream? That will become a dry stream. So that will dry out completely. Like that will be a dry stream, and that would be also dry well. So in that image, for example, like if you find your well is getting dry, that could be due to different reason, like due to change in that could be like because your water level is going down. Water level could go down because of less precipitation or because somebody is pumping. Like let's say uh, well, somebody installed like a big well here and he's pumping very much water, and he is like the groundwater is like dropped like this, so your water could also go dry here if a big well started to happen here with the normal like precipitation and recharge rate. Okay, so we talked about this. So here this is called like a gaining stream. Why this is a gaining stream? Because you see the head here, the head in the aquifer is higher than the head in the lake. Like your hydraulic head in the aquifer is higher than the hydraulic head in the lake. So this is like your head. So and then the water will flow from the aquifer to the lake. So and this would be called like a gaining like lake or like stream or whatever. This would be a gaining stream or a gaining lake. In that case, you see here, you have this is called like a losing stream. This is called like a losing stream because the aquifer, you see like your hydraulic head. So that's like your hydraulic head. Uh, Remember, water will always flow perpendicular to your hydraulic head. So you see like the hydraulic head here, yeah, is so that's like so the hydraulic head uh, here would be like that's like your hydraulic head here would be higher, like this would be like a higher value than here, and then water will flow in this direction. Here you could be like gaining and losing from one side. So in that side, so that's like your hydraulic head here. That's like your hydraulic head here. That's the contour of your hydraulic head. So like the water will flow perpendicular to your hydraulic head. So in that side it's like a gaining stream, and that side it's a losing stream. That's like your hydraulic head would be here. So that's like a gaining stream, and that would be like a losing stream. Here, that's a very complicated situation because you have like a groundwater divide here. So from this groundwater divide, like you see the water here like this, groundwater divide could include like due to precipitation, like you have a high rainfall event, so it created a groundwater mound here, and then you have a groundwater divide here. So some water, like at the top of this mound, some water will go here to your aquifer, and some water will go here to your lake. So and here, so this is a gaining stream. So this lake here, this is like your hydraulic head. That's your water table. This is like your water. And again, I want to see the difference between water table. This is like your hydraulic head here, water flow from the aquifer to the lake. But here you have this interesting situation. At this part of the lake, yeah? So at this part of the lake, the water will be like a losing lake. And at this part of the lake, it will be a gaining lake. And at this part of the lake, it will be, so here is gaining. Here is like losing. And here is gaining. Yeah? Because of this water mound here. So and then when we will learn this, we look at more of these example and later in details. But when you are a groundwater hydrologist and you go to the field to make your measurement, you will learn later how to make these measurements, and you need to keep this in mind. Now, one more thing here, uh, unlike potentiometric surface, the water table is influenced by the surface water body. So here, for example, you see these are some streams, and this is another stream. This is your lake, and this is another stream. See, this is your lake level, like the stages at your lake, and you see how they are the water table map of water table that is hydraulically connected to the lake or the stream. So and we've seen this here, like see this is a water table. In this case, see it's hydraulically connected to your stream. Even if you have like a Pershid lake, so this is a Pershid lake. Pershid lake means that, let's say this is like your lake is somewhere here, and you have a confining layer here, and so this is a confining like layer. We'll talk about this, and then this is your unconfined aquifer. So the lake is somehow not connected to the unconfined aquifer. So this is like your unconfined aquifer. But even though it is like this, you will still like, so you see here, like the lake level is not 310 like you will expect like this to be like similar to here, like you expect 310, but it's not 310, it's a little bit different. And downstream here, because the lake will still like water table map where the Pershid Lake water table is seeping from a Pershid Lake, so the water table contour bending downward. Because water table water will still seep, even this is a confining layer, water will still seep through here, and you see this bending here, like it will impact your water table. Versus, as I showed you before, like if this is a potentiometric surface, whatever is happening at the surface, whether this is like a connected lake or like a non-connected lake to your aquifer, it will never impact. Like so, even this is a connected lake, like it's unconnected to the aquifer, it is still like due to some uh, seepage from the lake. Is you see your water table is bending, like you would expect it like this one to be something like this, but it's a little bit bending because due to this little recharge that's getting from this lake. Similarly, if you have a pumping well, like so, if you have a pumping well, your water table will decline significantly. So this is like your normal water table, like 414, 412, 400. But once you start pumping, you see the water table will decrease significantly. And we looked at this here. So you see here, so this is your normal water table without pumping. Once I start pumping, your water table will decrease significantly, as you see here. So you see this contour like are far away because there's no big gradient, but once you start pumping, like this contour become like very dense and very close to one another because you start pumping. Okay, so that's also need to know. We talked about this. I'm just showing you like different images for it. So I told you that the water table will be influenced by your surface water bodies. But now here, what I told you before, I didn't tell you like the full truth. I was like kind of like it's not very rigorous in what I was saying. I told you before, like we have two types of aquifer. unconfined aquifer and confined aquifer. And unconfined aquifer, that is, it has like a water table, and the unconfined aquifer is directly connected to the water surface. The confined aquifer, it has a geometric surface and it is not directly connected to the land surface. So here you have a confining layer, here you have a confining layer. This part of the aquifer, like you see here, this is the transition point where, because this is your potentiometric surface, so here this is the zero gauge pressure. So this is like water table here, so this is water table here. Uh, uh, because see, this aquifer is exposed, yeah. Here, this is where you have a potentiometric surface. So that potentiometric surface start here because it's above, like the pressure here is like the pressure at your water level here is more than zero. The pressure 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 here is more than zero. Okay, so this we talked about. This is an unconfined aquifer. This is a confined aquifer. Well, actually, there's a third type of aquifer. Remember, like the Persian lake, you could also have a Persian aquifer. So a Persian aquifer, this is your typical unconfined aquifer, but above this one, you will find like this confining layer, and then you will find some little amount of water here. And that one could get dried very quickly because you only have this little amount of water. Once you start pumping this, that could get dried quickly, but it could also get recharged quickly. So so that's also one thing you need to bear in mind, that this could like fool you. You think that oh, this is like, see, this one is still like unconfined. This is still unconfined because this is still directly connected to the land surface. So water will come through here, water will come through here. This is not a fully confining layer, and and below this confining layer, you will see like this could be unsaturated. This could be like capillary fringe here. Yeah. So bear in mind that you could have like, this is called like a Persian aquifer, formed above the main water table on a low permeability layer in unsaturated zone. So you just have like a local, some low permeability layer that could hold an aquifer. And here, for example, that could, part of the spring discharge could occur from here. So from this Persian water table, so you have like this local small unconfining layer, and then you could get like spring discharge from here. Okay. So bear this in mind, but your main aquifer will is happening here. So you get this spring discharge, you might think, oh, like now I have an unconfined aquifer, and this is like this spring discharge is occurring due because of high pressure. But no, it's not. Doesn't need to be the same. That could be just like a Persian aquifer that is not like discharging to a lake or a stream and just discharging to the surface through spring or something. Okay. Uh, Now, last thing I want to do in this video before we stop is that I want to introduce like a new concept which is called transmissivity. We talked before about like hydraulic conductivity, okay? Now, transmissivity is like hydraulic conductivity time your aquifer thickness. So this has a unit like dimension of LT. Your aquifer thickness, so the aquifer thickness would be like here. So that would be like the aquifer thickness here, B. That would be like the aquifer thickness here. Here, that would be like the aquifer thickness here. That would be the aquifer thickness here. So transmissivity, that would be like, so the aquifer thickness, that will have a unit of length. So transmissivity will have a unit of L square over T. And the transmissivity, this is basically describes the capacity the transmission capacity of like your porous media, like the capacity to hold and transmit water. So transmissivity is generally like is generally used for unconfined aquifer. For confined aquifer, you still can use it, but it's not a very helpful term because like for for unconfined aquifer, once you start pumping, the water level will go down. And this B will change. But for for confined aquifer, once you start pumping, the saturated thickness will not change. Your saturated thickness will not change. This B will not change. The water level here will not change once you start pumping. Versus once you start pumping here, your water level will change. So that is generally like a useful term that we use uh, to understand like the rate at which water passes through like an unconfined aquifer. Yeah. Uh, and like if you want to put like remember like Darcy law. Darcy law, remember like Darcy law, we had something like this. So Darcy law, like Q, big Q is equal to negative K area time like your hydraulic gradient. Yeah. So you can also express it like this way. You can express it like big Q is equal to negative K. What is the area? So the area, that would be like the P, your thickness, your aquifer thickness times the width time the I. Yeah. So transmissivity can thus be defined as the amount of water transmitted horizontally through unit width of the unit gradient. So if you assume just like a unit width, like you assume like this would be like 1, like just unit width. So in that case, you can T, like if this is a unit width, like let's do this like this is like QB, this is a unit width, and this is I, then we'll have like Q prime, and then in that case, like this should be Q prime. Uh, uh, T will be equal to Q prime, and that would be the amount of water transmitted horizontally through unit widths under a unit gradient. Okay, so let's look here. So for the transmissivity for this is the water table, this is like your free surface, this is here your confining aquifer. Transmissivity of a confined aquifer, so in that case it doesn't make sense because like the water level will go down, so the H, so transmissivity of a confined aquifer, that would be K times H. See, the water level here like goes down, so H is not constant. Versus here, if I start pumping, this B will not change. Like what will it change would be like this level here. Like let's say I made another well here and I start pumping like this water level, but B here will be constant. Yeah, it will not change. So transmissivity for a confined aquifer, that would be like T times K, and this is saturated thickness. So here this is saturated thickness. That's a saturated thickness. Let me clean this. While like the saturated thickness here, it changed. Like once I start pumping, then the H will drop. My head will drop. Yeah, and the saturated thickness will change. Okay, so let's look at this example. So here what else do I want to say here? Yeah, yeah. So basically, like T1 here, like let's say if K is constant here, like K is constant here, then T here and the aquifer thickness is constant, then transmissivity here will be equal to transmissivity. Sometimes this might not be constant, so sometimes the B will not be constant. Like you have like the layer is like it's thick here, and then as you move forward, it could be this layer, yeah. So you get more confining layer here. So you get like the confining layer could be bigger. I mean, I showed you an example here, like you see here, like see B here is different than B here is different like than B here. So like B1 is bigger than B2 is bigger than B3, but this B itself does not change. Like this thickness will not change. Like once you start pumping the water, like this saturated thickness will not change. It could be different, like a different part of the aquifer, but the value, like this B1, B2, B3 will not change. Unlike here, the head here will like once I start pumping, so this is the head here, this is the head here. This is like if you consider like this head value could change, like or this water level value could change. Okay. So let's look at this example like aquifer, like you have two aquifer, aquifer 1 and aquifer 2. This is both are confined aquifer with a hydraulic conductivity like 100 meter per day and thickness of 10 meters. So you have this hydraulic conductivity and this thickness. So K1, this I will just call it for aquifer 1 is like 100 meter per day, and the B1 is like 10 meter. That's one. Aquifer 2 is also a confined aquifer that has a hydraulic conductivity. So K2 is mean. What does mean lower hydraulic conductivity mean? Lower hydraulic conductivity means it has it can its ability to transmit water is like stored like and transmit water is lower than this one. So this one has lower hydraulic conductivity. It cannot like conduct or transmit water as good as this one. But this one has a B2, like it's very thick. Like this one is like little bit only 10 meter, while this aquifer is like 30 meter thick. So here my question to you, which aquifer can transmit water more, like this guy or this guy? Well, to know this, we can just calculate transmissivity. So transmissivity is K time B. So if you did this for like, so transmissivity for this guy, so if you multiplied like these two, so for this guy here, you will get 10 to the power minus 3 meter square per day. That's how much water will flow in a unit width under a unit change in head per day for this guy. How about this one? How much water can be transmitted by this guy? So by this guy, if you multiplied like 50 times this guy, then you get about like 1.5, 10 to the power 4 meter cube per meter, sorry, meter square per day. Yeah. No, sorry, 10 to the power 3, not to the power 4. Oops. No, no, that's correct. Yeah, that's 10 to the power 4. Yeah, so that's like an order of magnitude, like about 15 times more that this one can transmit, even though it has a lower hydraulic conductivity, but because it is thicker. So T2 is higher than T1, which tells that Aquifer 2 is better target for like wet water supply well because it's much higher transmissivity, so it yields greater production and like less drawdown. It will have greater production uh, than this one. Like so, Aquifer 2 will have a greater production than Aquifer 1. Let's look at another example. This is the last slide that I have here. Sometimes your aquifer, like so, this is your confining layer, yeah, and this is like your confining layer. But here you could have like different like aquifer types, like layers, thickness, with different transmissivity. So in this example, for example, like the lower layer is about, so the lower layer here, yeah, it's about like 20 meter, and the hydraulic conductivity of this one is like about 30 meter per day. Then the unit above it here is, so this is 30. So this from here to here, that's like 30 meter. The unit above it is like 10 meter, and the hydraulic conductivity here is 60 meter per day. The unit above it here, which is like 20 meter, yeah, you get here like this is 20 meter, like this is B, like B. So here B, this is B1, B2, B3, and this is here K1, K2. What is the K3, or like what's the hydraulic conductivity? K3 is equal to here, like you see here, that's like 10 meter per day. And then finally, the last unit here, that's a 20 meter, like B4, is like 40 meter, and the hydraulic conductivity K4, I think you read it from here, it's about 4. K4 is like uh, 4, sorry, I have typos here. This is only one. So this is one, this is six, and this is three. So K4, that would be equal to 4 meter per day. Yeah. So I could just find like the average like transmissivity for this unit. So the average transmissivity for this unit would be the arithmetic mean of each of these values. So that's like B1 times K1, B2 times K2, B3 times K3, B4 times K4, and that will be get here. So the transmissivity for this unit, that would be 250 meter cube per day. Okay, so I think that's all for this lesson. That was just like a quantitative understanding, qualitative understanding, so you will know what is confined, what's an unconfined aquifer, what's the difference between a water table versus a bathymetric surface. That's one of the key points to understand. Water table goes up and down, the piezometric surface. uh, so as the water table go up and down, your water level will go up and down. While like as the piezometric surface will go up and down, your water level will not go up and down. Your water, like your aquifer, will be remain saturated unless you manage somehow to dewater this aquifer and drain it completely. But this is not generally the case, yeah. But then your water table like will go down, yeah, and then that might act differently than a confined aquifer. So the main also thing you need to learn is a confined aquifer. When you pump this water out, you dewater the aquifer, so you empty the pores versus like in the this unconfined aquifer versus in a confined aquifer, you release water when you start pumping the water out. This water is under pressure, so you just release water from pressure, like you release some of the compressed water and the other water will expand. And we will look at this quantitatively in the next like upcoming lessons. Yeah. So that is all for this lesson. You should know what's a confined, unconfined aquifer, what's the water table, what's the piezometric surface, and then later on we will learn how these are related to head, your ground, your hydraulic head. Yeah. And I think that's all. Perched aquifer, you should know this also, like this term from this lesson. I think this is the main part. So please, yeah, feel free to watch it again. If something is unclear, ask me or ask generative AI. Like you can chat with generative AI. I'm not sure how accurate they will be in providing these type of information. So ask ChatGPT or any generative AIs that use. Uh, Ask the instructor or get like one of the textbooks that I recommended and read it. Yeah, let's see here. Like remember here at the beginning, I have like two recommended textbook. This one is available for you. You can read it for free. This one you need to buy. This is the recommended textbook for the course. But whether you read like these chapters or this chapter, you will find much more information that I'm providing, and you will learn this in detail and in depth. So I highly recommend, yeah, I would recommend that you read some of this chapter. If you don't want to buy the book, just read it from here for free. Okay, so I think that's all for this video, and like see you in the next video. I leave you with these two books. Okay.